In this video, we will introduce a new camera offset space and present a novel potentially visible set method operating in this space. Providing low latency and high fidelity VR experience while maintaining mobility is currently an impossible task. Current solutions always fall short on one of these aspects. High quality, low latency head-mounted displays need to be bound by thick cables. Wireless HMDs manage only scenes with modest fidelity, and the remote renderers suffer from latency, which is intolerable in VR scenario. Our work focuses on the context of remote rendering, where a powerful server computes data on the fly and transfers it to the client. The approach we are about to present is applicable both to tethered and wireless HMD displays. The main problem of streaming rendering is the frame rate of the server. VR applications require high frame rate output, which the server cannot fulfill. Incorrect frames are thus presented to the user, which drastically degrades the experience and can lead even to motion sickness. The user's movement in VR often includes rapid and large view offsets. State-of-the-art uses image-based rendering methods to extrapolate a novel view when the server frame is missing. The current solutions suffer from visual artifacts and can manage only small view offsets. We propose a server frame data structure from which the client can extrapolate a correct novel view. Our server frame consists of potentially visible geometry and its corresponding shading data. These are both transferred to the client, which then extrapolates the novel view by rendering the geometry using the provided shading information. In this paper, we focus on the first part of the server frame. For a specific area around the camera, we want to guarantee a correct and fast novel view under any camera offset and angle. Thus, we need a potentially visible set algorithm that works on the fly without pre-processing on a dynamic stream of data. To our knowledge, there was no such algorithm, until now. Moving your head in a VR scene includes both translation and rotation. If we would accept only the exact visible geometry set, the solution would introduce disocclusions and out-of-frame errors. Thus, we need to include geometry that may potentially become visible under the camera offset we decided to support. The first step of our method is increased field of view. This allows us to mitigate the out-of-frame artifacts. Then we cull away the backfacing and out-of-frustum geometry. From the remaining geometry, we construct a per-pixel fragment list. Let's choose a sample pixel. If we were to shoot a ray from the camera's position through the pixel center, all triangles this ray penetrates end up in one fragment list. Each entry in the list represents one triangle in the scene. Naturally, the parts of the scene with more overlap in geometry create longer lists. At this moment, each entry in the list represents a triangle that exactly covers the given fragment. In order to support also triangles that potentially cover the fragment under an offset, we enlarge the existing geometry. Enlarging the geometry is a simple screen space convolution using a kernel of the supported offset size. We construct the fragment lists from the enlarged geometry. This significantly increases the length of lists. In order to determine per triangle visibility, we introduce camera offset space, or COS. Each fragment list contains triangles corresponding to one sample location, the fragment coordinates. Similarly, the camera offset space is unique per each sample location, thus unique per each fragment list. The COS tells us under which camera offsets does the triangle cover the sample. We transform every triangle in the list into its corresponding COS representation and solve the visibility there. Let's pick a sample fragment list and observe its COS representation. Let's highlight the supported camera offsets. The resulting shape depicts the supported camera offset boundary in COS. We form occluder regions based on the edge connectivity in the COS space. Then we classify each edge of each triangle by its relation to the camera boundary as inside, outside, or intersecting, and with the help of sample points determined per triangle visibility. For details, see our paper. So far, the visibility was considered under a given sample, the fragment coordinates. This can introduce missing geometry appearing in between samples, which is best demonstrated on fine geometry. In order to provide a hole-free solution, we enhance the camera offset space by 2 additional dimensions representing the subpixel offset. Computing the visibility afterwards is more challenging, but still doable. For details, we again refer to the paper. Adding the subpixel offset enables us to run the fragment list construction in reduced resolution and also adds support for rotation. With rotation support, it is possible to compute the potentially visible set for a 3D region from multiple 2D regions, similar to cube mapping. This concludes the potentially visible set algorithm. To our knowledge, there is no potentially visible set algorithm that would work on the fly without pre-processing triangle connectivity information or information about which triangles make up an object. We have evaluated our approach on 4 scenes. The most challenging scene contains millions of triangles and provides many difficult test cases to tackle, such as thin geometric structures, disjoint structures, and slanted triangles. Our method handles all of these cases. In addition to evaluating our method on full geometry, we also measured the performance for level of detail geometry, as it is commonly used in frame rate sensitive 3D applications. In order to provide a comparison of the novel view extrapolation, we implemented a simple object space shading on the potentially visible mesh. Even if we compute the server frames of other image-based rendering approaches in increased resolution and wider field of view, our method provides higher fidelity, higher frame rates, and much larger view offsets. The fact that the client has geometry information at disposal opens up possibilities to address 2 major drawbacks of the image-based rendering methods: transparency and view-dependent shading. Multiple ways to address the view-dependent shading exist, the simplest being splitting the shading information into view-dependent and view-independent parts, where the server computes the diffuse component and the client, depending on its computational capability, can compute the view-dependent part. In order to support transparency, transparent objects are simply not considered an occluder in the visibility resolution step. Thank you for watching.